Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture number 8 of the course Robot Motion Planning. In the last class we had looked at configuration space, and today we'll move on from there and look at C-space obstacles. That is, when we have obstacles of different shapes, then how do we construct the corresponding C-space. Okay, then we'll move on to the C-space for serial arm robots. Okay, very quickly revising what we had done in the last class, we were talking about C-space. What is C-space, and then we'll move on to C-space obstacles. So in the last class we saw that when we talk about a mobile robot, we essentially mean that a mobile robot should not hit an obstacle when it finds the path. Okay, so and to do that, what we saw, the various examples that we looked at, the robot was a point robot. It did not have any physical dimension, for example in the case of the bug algorithm. Okay, now real robots have physical dimensions, which means that they are not a point. Okay. Now, so the question is how to specify all the points in a robot. Okay, and that is what we are trying to look at. And to do that, we go to the configuration space. Now, we see that two parameters are enough to specify all the points of a robot that can only translate. For example, if I have a robot like this and I know its radius, I know its center x and y, and I don't know the radius r, then it automatically means that if I know where is x, y, and I know what is r, so I basically know that if the point is here, x dashed, y dashed, then I know all the points inside the robot because I know the radius r. So indirectly, I know all the points in the robot. So basically, just knowing x and y is enough to find out where all the points of the robot are lying. Okay. And these two parameters, x and y in this case, they make up the configuration of the robot. This for a mobile robot. Please remember, this is a mobile robot that can translate. Okay. Now, the configuration space or C-space is the space of all the configurations of the robot. What is the configuration of the robot? The configuration of the robot is x and y, because knowing x and y, we know where are the location of the other points of the robot. So the configuration is just a point in the C-space. Okay. So, for example, if you have a workspace like this and you have a mobile robot which has a radius of r, okay, then how do we make the C-space? We basically shrink the robot to a point. So the robot becomes a point here, and this comes inside by r. So this becomes smaller by a distance r, and that is my C-space now. So this space becomes my C-space, and the robot becomes a point in the C-space. Okay. Now this looks like the Cartesian space. For example, this is x and y. Similarly, this is x and y. So they look similar, but they are different spaces. So the path planning is essentially, we are trying to find the path for a point robot now, because the robot has shrunk to a point and the workspace has become smaller. Okay. Now the configuration of the C-space looks like Cartesian space, but it is not the same. Okay, please remember that. Now, what is the degree of freedom of a system and how is it related to the configuration space? Okay. So the degree of freedom of a system is the dimension of the configuration space. In the previous case, we saw in the case of the mobile robot, we had x and y, and we said that x and y is enough to specify the configuration of the system. Okay, so in this particular case, this is 2 degrees of freedom for the robot, which has 2 degrees of freedom because it can only translate, and the configuration space also has 2 degrees of freedom. Okay, so the robot and the dimension of the configuration space is 2, which is x and y. Okay, so if we have a point robot, its configuration will have a dimension of 2. So if I have 3 independent point robots, for example, we talk about swarm robots and multi-agent systems. So I have 3 robots here now. This is x1, y1, this is x2, y2, this is x3, y3. So these are the configurations of these 3 robots. Now they are independent, means they are not connected in any way. Okay. So what is the total configuration? What is the total degrees of freedom of the system? Now it is 2 plus 2 plus 2, which is equal to 6. Okay. So please note that these are 3 points which are independent, each of them having 2 degrees of freedom. So the total degree of freedom of the system is 6. Okay, they are not connected in any way. Okay. Now, a robot that can translate and rotate, minimum number of parameters required to specify the configuration. Okay, in the previous case, we said that it can only translate, it cannot rotate. But if you have a robot which can translate and rotate, then how many degrees of freedom are required? Okay, so how do we, let me draw such a robot. Now, this is a robot here, and we have a wheel, okay, two wheels, okay. And let's say it has a caster wheel. There is a caster wheel there. Okay, so this is omega 1, omega 2. Now we need a global frame. This is my x-axis, that's my y-axis. Okay. Now in between the two wheels, let's take a point P, which has coordinate xy. Okay. Now I put a local frame here, which is in this direction x dashed, and that is my y dashed. And this is my angle theta. Okay. Now what is the degree of freedom of this system now? Now this robot can translate and it can also rotate. So what is the degrees of freedom of this system? How do you define that? Okay. Now let us say that how many parameters are required to fix the position and orientation of this system, of this mobile robot. Now let us say we have 3 points. Let us assume these 3 points A, B and C. So the first point A can be placed anywhere on this robot. Okay, so I can place my point A here, for example. Okay, this is my point A. How many degrees of freedom it has? It has 2 x and y. Okay. So it could be anywhere on this body of this robot. Now next, I want to place the point B. Now the point B is, let me say here. So this distance is this is my point B. So this is XA, YA, this is XB and YB. Okay. Now the distance between A and B is fixed. So the distance AB is fixed, and hence the distance between this is XA minus XB squared plus YA minus YB squared. Okay, that's the distance between A and B. So where could this point B lie? It can lie on a radius which is having a distance AB. So anywhere on this radius, this point can lie. Okay. So I have fixed my point A, which could lie anywhere. Now the point B must have a fixed distance from point A, which is given by this distance. But that is not enough to, this point B could lie anywhere on the radius here, on the circular radius, right? B could lie here, B could lie here, B could lie here, and the distance would still be the same. Okay. Now to fix that, that basically means that I need another point, I need the point C. So I've got my point C, so this is XC and YC. Okay. Now if I say that the distance A to B is this distance, the distance B to C and the distance A to C now gets fixed. Okay, the point B, the moment I say that the distance AB is a constant distance and the point B could be anywhere on the circle. Now the moment I put the third point, that is C, and I say the distance between AB, AC gets fixed, then the orientation of the body also gets fixed. Okay, so the position has got fixed and the orientation of the body has also got fixed. Okay. If I have only 2 points A and B, the orientation is not fixed. Why? Because this point B could be anywhere, so it could be rotating, right? But the moment I put my point C, now the position and orientation of this body gets fixed. Now what about the distance? So the distance AC is equal to XA minus XC squared plus YA minus YC squared. Okay. And the distance BC is equal to XB minus XC squared plus YB minus YC squared. Okay. So that means you need 3 points to fix the position and orientation of a body. You can get 2 points to fix the position, but you cannot fix the orientation because it can still rotate and it can still maintain the distance AB. But the moment I put the point C, now the orientation also gets fixed. Okay. So this means how many degrees of freedom are there? 2 plus 2 plus 2, which is equal to 6. Okay. But now we have put these constraints. There is one constraint here, second constraint here, and the third constraint here. Okay. Now the moment I put this distance constraint between those 3 points, so it reduces the degrees of freedom of the system. So it becomes 6 minus 3 constraints, which is becoming 3 degrees of freedom. So this robot which can rotate and translate has 3 degrees of freedom, x, y, and theta. Okay. Now something to remember here is that this type of constraints are called holonomic constraints. So a holonomic constraint is one that can be expressed as a function of the configuration variables and possibly time. So I can write this distance in the form of g, q, t is equal to 0, or just in terms of G and Q, which is equal to T. Okay, so this constraints, this distance constraints, okay, are called holonomic constraints, and each linearly independent holonomic constraint reduces the dimension of the system configuration space by 1. Okay, that means in the previous case we had 3 points ABC which had 6 degrees of freedom if they were independent, remember, but we have 3 constraints now. Okay, those 3 distance constraints, so my degree of freedom of the system has become 3 dy. Okay, so this type of constraints, which are distance constraints, are called holonomic constraints, and they reduce the dimension of the configuration space by 1. So if there are 3 constraints, it will reduce by 3. So this becomes totally 3 degrees of freedom. We have another kind of constraint which is called a non-holonomic constraint. Now suppose we have a car here. Let's imagine this car, and we have a wheel, and it has turning wheels in front. Okay. Now this is my global frame X, and that's my Y. This remains same. Now let me say I fix my axis like this. This is the center point. That is the point P, which has XY coordinates. Okay. So this is my x-axis. That's my y-axis, x dashed, y dashed. Now this is now there is an angle there. Okay, so there is my axle and there is the angle. So that is my phi, which is my turning angle. Okay. Now, when the car is turning, please note that when the car is turning, this is turning now. This point is having a curve. Okay, but at every point on the curve, the velocity vector will be in this direction. That's my v. This is theta. Okay, theta is the angle here. Okay, with the x-axis. Okay, this is my x. Okay, so at this instant, when the car is turning, although the car is turning, at that point, every point, the velocity vector is going to be tangential to the curve. Okay, which means that this velocity vector will have 2 components. So dx by dt will be equal to, in the x direction, it will be v cos theta, and dy by dt is equal to v sin theta. So this velocity vector will have 2 components, one along the x direction, one along the y direction, given like this. So when I divide, if I call this equation 1 and equation 2, so dividing 1 and 2, what we do get is dx by dy is equal to cos theta by sin theta, which implies that sin theta into dx minus dy into cos theta is equal to 0. Okay. Which means that at every point on the curve, the velocity vector has to be tangential at that point. Okay, which means that we have put in a constraint like this. Now this is a velocity constraint. Okay. In the previous case, we saw there were position constraints in terms of distance. Here, this is in terms of the velocity now. And this type of constraints are called non-holonomic constraints. They are velocity constraints, okay, and they do not reduce the dimension of the system configuration space. So in this particular case, although this robot or this mobile robot has 3 degrees of freedom, we have seen, okay, and it also has a velocity constraint like this, a non-holonomic constraint in terms of velocity. It doesn't decrease the dimension of the configuration space below 3. Okay. So there are 2 kinds of constraints we have seen, holonomic and non-holonomic constraints. We'll come to this in more detail when we come towards the end, when we do motion planning with holonomic and non-holonomic constraints. Okay. Now the degree of freedom for a robot, or dimension of the configuration space of a robot which has drive and steering. Okay, let us have a look at that. So here we have seen that the robot which has drive and steering, we just saw that robot, and it has a steering. So there is my steering angle here. So this is my steering angle, which is phi. So this robot has dimension 3. Okay, so the configuration of this robot is will be represented by t theta, where t is corresponding to x and y, and theta is my in this particular case is the orientation. So this is my 3 degree of freedom system. Okay. Now, although there is a velocity constraint, it does not decrease the dimension of the configuration space. Okay. Now, what is the angle between the global frame and the local frame? That we have seen, that we know that there is a rotation matrix there. Okay. So the angle between the global frame, so if I draw my global frame here, so my global frame is x and that's my y, then the relation between x, y and x dashed y dashed is given by the rotation matrix R. You know what is the rotation matrix? It's a relation about z. So it's cos theta minus sin theta cos theta. Okay, that's 0, 0, 1 and this is 0, 0, right? So this is basically to explain the configuration of the mobile robot, which has rotation as well as which has got drive and steering. Okay, and this is something which we did in the last class. How do we draw the configuration space? Today's class is about C-space obstacles, so we're going to make C-space obstacles for different shapes. In this particular case, we see that because the robot is a point robot, the configuration space shape remains the same. In this particular case on the top, that is in case 2, we see that the robot is going to go and sit like this, and what happens is the shape of the obstacle becomes enlarged. And at the corners, I explained last time that when the robot goes and sits there, it's like exactly at that corner point, the robot can rotate like that because it's a point contact, right? So there's a curve. That's how we get these curves. Okay. In the third case, we have seen this robot is slightly larger, so it is a bigger robot. So it goes and sits like this, and the shape of the configuration space becomes like this. Okay. So basically, we go and put the robot wherever it can go and sit, the maximum it can go, and we draw the locus of the center of the robot. That's how we get the C space. So this is my C space obstacle. Okay. Now we also looked at the case where we have a mobile robot like this, and we have an obstacle which is shaped like this. How did we get the shape of the C space obstacle? We basically imagine the robot to be going and sitting at all these points, the maximum position to which it can go and sit. So it can go here, it can go here, it can go here. Okay, and wherever is the center of the robot, that is the maximum it can go. So we draw the locus of the center points, and our shape of the obstacle becomes like this. Okay, it is like the robot is a circular robot, so it's going and sitting there, and it can go and hence the obstacle increases to this shape. Now you can visualize this very clearly, and this is simplified. Why is it simplified? For the very simple reason that it was a circle, and the circle is shrinking to a point. Okay, so it is like there is no rotation. The circle doesn't have a rotation, because even if it does rotate, it's still a circle. Okay, so you can see the difference between a triangular robot like this and a circular robot. So in a triangular robot, if the robot rotates, it will change, the complete shape will change. It will become like this, that you can imagine. But a circular robot, even if it rotates, it still remains a circle. There's no change in the shape. So first we'll start off by looking at circular robots, which is easier to understand. Then we'll go on to triangular and other shapes. Okay, so next, let's look at a triangular robot. Okay, I hope you understand how we got this shape. It's very easy. At the points, at the corner points, you have to be careful, because at that point, the robot can actually rotate about that point. And that's how you get these curves. Okay, otherwise it's a straight line. Okay, now let's look at a triangular robot. Now this is the triangular robot, which is shown here. And it is right angled. Now something to note very carefully, please note, you're supposed to note the number 1 is the origin of axis. Where is the origin of the frame? The origin of the frame is here. Please note that very carefully, because the shape will depend on that origin wherever it is. If you change the origin, the shape will change. Okay. Now let us imagine this robot can translate in 2D. Okay, that means the triangle, we start off by saying that theta is equal to theta 1. Okay, and we keep this theta is fixed. It does not rotate. Okay, something very, very important. So we start off from here. My origin point is here. Okay, so I can translate it by going forward like this. So it can go right till the top. Okay, so the robot has come here. I hope you can imagine it's translating and it's going up. So this is my robot at that position. This is my robot at this position. What am I tracing? I'm tracing the origin of that local frame there, which is given by O. So what is the line traced by the origin? It is tracing like this, going till here. Okay. Now it can go right. Okay, so it has gone right on top there. Now I push it this side. So it is going here, then it has gone here, then it has gone here, then it has gone here. Okay, so what do I get? The origin is tracing again this line. Okay. but at this point it cannot go down. Okay. So it has to go forward a little bit more. Now you can see it has gone forward till there. Only then it can come down, because it's a physical body, right? It cannot go inside the obstacle. So this is my obstacle. Now it has gone towards the right. Now it can slide down. It is sliding down. It has come till here. Okay, right. Now something to be careful about. Once it is here, okay, at this location, this is an inclined edge. So it can slide along the inclined edge and come here. So what do you get here is this shape. The locus now becomes like this. That means I started from here, I went there, then I went there, I went down. But here it is sliding down. So the origin is moving along this line. Please note that carefully. The origin is moving along this line. Okay, and it comes till here now. Now this is my origin there. Again, the origin can go left like this. Okay, and then I trace. So what did I trace? I traced this, 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 and that. That is my shape of the C-space obstacle. Okay, so I'll repeat this again, because it's very, very important that you should know how to do this by yourself. It just takes a bit of practice, and that's all. So I'll repeat this again, so that everything becomes clear from here. Okay, so in the previous case, what did we do? I took the circle. So let me come here. So what did I do is I took the circle and I placed the circle on the boundary, right? And then I traced the CG of the circle, or the center of the circle. What did I get? Here I get a curve. I get a straight line here. I get a curve here, straight line, curve, and that is my shape. So the shape of the obstacle becomes this. Now it is like saying I took the circle and I moved the circle along the boundary like this. Okay. Now similarly here, the robot is not a circle, but it's a triangle, and the origin is fixed at this point. Okay, that means I'm tracking the origin basically. In the previous case, I was tracking the CG. Okay, so this was my origin in the previous case. That's my XY. Okay, so I was tracking the center point there. Now I'm tracking the origin, which is at the tip of the robot. Theta is fixed. It does not rotate. It only translates. So I start off from the corner here. So I place my robot there, and it can only translate, so it can go up like this. Okay, so these points you can see that it is going up. And which point is being tracked? The origin is being tracked, so it is a straight line. Okay, so it is going right up till here, because until it goes up till there, you can move it towards the right. So which line did it trace? It traced this line. Right. Now I take it on the right side, it goes till there. Okay, and then I bring it down. So now I bring it down, it comes till here. So this point is being traced. Now at this location, because there is a curve, there is a slant edge there. This is a slant edge. This can come down like this. It comes down like that. The robot comes to this configuration. Okay, so it has come down like this. Then it has gone like this again. Okay, so what was the trajectory of that origin? It is like this, like this, like this, like this. Please note that curve there. Okay, so my configuration space has this shape now. Okay. Please note that there is one incline here. Okay, the other places it's rectangular, it's 90 degrees only. Whereas here there is an incline. This incline corresponds to what? This incline corresponds to this side. Okay. So now, so this is for a fixed orientation. Let's say this is theta equal to 0 degrees. Okay. Let's simply say it is equal to 0 degrees. Now suppose I change the theta. So this was theta equal to 0 degrees, something we did just now. Suppose I change the theta. Suppose I make theta equal to 45 degrees now. 45 degrees means, and this fellow is bent now. Let's say that is 45 degrees. Okay. Now you see, again, please note, where is the origin? The origin is here only. Okay. Now, will the shape be the same as before of the C-space obstacle? No, it won't. Why? Because this fellow is rotated now. Now you also appreciate, in the case of a circle, it's much easier. That's why mobile robots are all circular. You can draw this C-space very easily. Okay. Now let's start drawing this from here. So I place it here. This is my origin. The tip of that robot is my origin. Now I move it upward like that. The robot moves up. It's moving up and it goes right till there. Okay, it goes till here. There. Okay, so I get this surface. Now at this location, I can slide the robot forward. It is sliding forward like this and going here. That means it can always slide along an inclined edge. Okay, so now it has slid like this and gone here. Now you move it right, it has gone till here. Now there is another edge here. So what it can do is it can slide like this. So we are marking the tip, right? We are taking the locus of the tip. So this part comes here. Then it goes down. Okay, it has come to this location. Now it can slide again and come down. So it is sliding down, so we're getting this surface. And once you get that surface, then you slide it leftward and it comes here. So what is the shape? It is this. So this is my shape. Now please note, in the previous case, when the robot theta was equal to 0 degrees, you had one inclined face only, the C obstacle space. Okay, in the C obstacle, not C space. In this particular case, we are seeing that there are three inclinations. There is one here, and one there. And you should exactly figure out how they have come. Okay, I'll repeat it again because this is something very, very important. Please do it by yourself once, it will become very clear. If it is still not clear to you, what I would suggest is that cut a paper in this shape of a triangle, and then you have an obstacle which is rectangular. You move this paper triangular robot around and see which is the locus of the points tracked by the origin of the robot. Okay, it becomes very easy then. So I'll start again. We have this robot which is inclined at a particular angle, let's say 45 degrees. So I start drawing this. I start from here always. Okay, there it is. Where is the origin? The origin is at the tip here. So I'm going to track the locus of the motion of the origin. So what do I do here? I move it upward. So I move it up till where? I move it up till here. Okay, so it has gone up till there. Okay. Now, once it has gone up here, you can slide it along one inclined edge, because you can slide this so it goes up like that. Then you move it rightwards. It goes till the end there. Now here you can slide it again in this direction because of the inclined edge. So it comes down like this till here. Move it down, it comes to this point. Okay, and once it comes to this point, then what we can do is we can slide it along this edge, and it comes here. And then I move it left, it comes here. So what is the shape? Shape is like this, like this, like this, like this, which is this one. Okay, the C space obstacle shape is given here. Now there were three inclined edges. Okay, so on this case also you're getting three inclined surfaces here, one here, two here, and third here. Okay, so there is some correlation between the inclined surfaces of the robot and in the C space obstacle, or the C obstacle, where the inclined faces are going to come. Okay. And there is an algorithm which is called the star algorithm, because which can automatically find out, or which is an indicator and can help you how to get the actual shape of the C space obstacle. So let's take the example of this robot here, which is at, let's say, theta is equal to 45 degrees. The robot has rotated by 45 degrees. Okay. Now in this robot, what we are doing is we see there are three inclined faces. Okay. Now in each of the inclined faces, we draw this perpendicular. This is R1, R2, and R3. Okay. So R1, R2, R3, R1, R2, and R3 are perpendicular to edges or sides. Okay. So you have R1, R2, and R3. Now on the obstacle, this is my obstacle. This is my obstacle. In the obstacle also, on each of the edge, I draw perpendicular E1, E2, E3. So E1, E2, E3, E4 are perpendicular to edges again of obstacle. This is case of robot. This is case of obstacle. Then I make this diagram. What is this diagram? I start E1, E2, E3, E4. I arrange it like this. This is E1. This is E2 clockwise, E2, E3, and E4. Okay, so this is going clockwise. Okay, so I put my E1, E2, E3, E4. Then I take my R1, R2, R3, R4. So first what do? Place E1, E2, E3, E4 on a circle. Okay. Then what do? I take my R1, R2, R3. Then I take R1, R2, R3. The directions are already given. Look at the direction of E1. E1 is in this direction. This E1 is also in that direction. So it maintains the same direction. Then what do I take? R1, R2. I maintain this distance, this directions. R1 is this side. That's my R1. R2 is that side. This is my R2. And this is my R3, which is here. Okay. So I place my R1, R2, R3 in circle along the same directions in which they originally are there. Now I start drawing my C-space obstacle. Okay, this is my C-space obstacle. So this gives us an indicator of where that inclined surface will be. So let's look at R1. R1 is between E2 and E3. Where is E2 and E3? So E2 is here and E3 is there. So R1 is here, in between here. Okay, so and R1 corresponds to which side? R1 corresponds to this side. Okay, so this incline will come where? It will come between E2 and E3. Okay, so where is E2 and E3? E2 is here, E3 is here, so it will come here now. Okay, so it will, so on my C-space obstacle, this will come here. Okay, so that is because of R1 between E2 and E3. Okay, that inclined surface. So we'll get this inclined face there. Okay, so this is my inclined face. This is corresponding to which side of the robot? That R1 side. Next, let me catch the next one. Let me say, sorry, we are going clockwise, right? So in between 3 and 4, there is nothing. So there is no inclined face between 3 and 4. Where is 3 and 4? Here. 3 is here, 4 is here. So here there is no inclined face. You can see that. The next one is R2. R2 is between E4 and E1. So where is E4? E4 is here and E1 is there. And R2 is coming there. Where is R2? R2 is this space. That means it will come there. Okay, so you can see it is coming there. So that one is because of R2. So this is because of R2. There is nothing here. This is because of R1. And now let's look at, we are left between E1 and E2. So E1 and E2 we are left, and there is R3. So R3 comes between E1 and E2. So R3 is in between E1 and E2. So where is E1? E1 is here, E2 is here. So R3 is coming there. And R3 corresponds to which edge? It corresponds to this edge. So my angle will come there. That much will come there. So what is the shape I get? I get this shape, this, this, and that. That is this one. So I get one here, I get one here, I get one there, I get nothing here. That's the shape. So this basically gave us an idea of how to draw this shape and where those inclines will come, to be done automatically. This is another example. In this particular case, the robot, we can say, is not rotated, so theta is equal to 0 degrees. I follow the same procedure. I start with E1, E2, E3, E4. These are perpendicular to the, okay, so I first mark E1, E2, E3 and E4. They are perpendicular to edges of obstacle. Okay, next what we do is I take the robot and I mark R1, R2, R3, R4, which are perpendicular to edges of the robot. 1, R2, R3, perpendicular to edge of robot. Okay, then I draw my circle, which is here. So I mark E1, E2, E3 and E4, and I place my R1, R2, R3, R4. So this is my R1, R1. Please note R1 isn't here now, R1, R2, because R1, R2 are perpendicular to the edges, and the edges are perpendicular to XY axis. Okay, R3 is here only. Okay, please note R1, R2 and R3 where they are. Now we start drawing the inclined surfaces. Okay. So I start off between E2 and E3. So E2 and E3, E2 and E3. So there is something there. Okay, what is there? R3 is there. What is the angle here? The inclined surface is there. So I get this surface there. Okay, so which is here. Right. Now next, what do? We go to E3 and E4. So where is E3 and E4? E3 and E4. R2 is along E4. Okay. So R2 is along E4, which basically means that it is not coming in between E3 and E4. It is along E4 only, along the edge E4. Okay. So this will not cause any inclined. It is like saying it is a straight line here. Okay. It is not an inclined line. Similarly, R1 is along E1. Okay. So it is going to be this one. Okay. It is not going to cause any angle there. Okay. So if there is an angle, it will cause an inclined surface on the C obstacle only if the edge is inclined. In the previous case, if you see, this edge, R1, R2, R3, they were all inclined. Okay, if you can imagine, this is my x-axis, that's my y-axis. So if an edge is perpendicular to this or perpendicular to this, it will not cause any angle on the other side. Only if it is inclined, then it will cause an angle. Okay. So this is the shape. There is only one inclination. R1 is along E1 and R2 is along E4. So there is only one inclination. So my C space obstacle. So this is my C obstacle. So this is my C obstacle. Okay. So this is the shape of my C obstacle. I hope it's clear how things are done. Now, this will give you an idea that for a circular robot, it's pretty easy. Okay, because the circular robot, there is no orientation. Even if the robot is rotating, it is still a circle. Okay, so there is no change in the C space obstacle. But in the case of a triangular robot or any other shape, if it starts rotating, then what will happen? The shape of the configuration space obstacle will change. Okay. That means for every rotation, the shape of the obstacle will be different. Okay. So what we can do is, we can start off by saying that this robot starts with theta is equal to 0 degrees, change by 1 degree, okay, up to 360 degrees. And for each of these particular degrees, you'll get a particular shape of the obstacle, C space obstacle. Now you combine all of those and you get the total shape of what the total C space obstacle will look like for the translating and rotating system. So in this particular case, the robot is faced like this. Then we rotate the robot a little bit, maybe we make it like this. Then we rotate a little bit more, make it like this. Then we make it like this. Then we make it downwards. Okay. So we rotate from 0 degrees to 360 degrees. And for each of those, you get a particular shape. So you stack those shapes. Say, for example, this is theta equal to 0. That is theta equal to 360, it will be the same shape, 359 degrees. So you stack them all together, and this is what we call a volume. So this is a volume bounded by patches of ruled surfaces. Okay. So a polygonal robot translating and rotating in 2D space is actually, you'll be getting a volume. A C space obstacle is a volume bounded by patched ruled surfaces. So if you're doing motion planning where the robot is also rotating and translating, it becomes pretty complicated because it will start moving here now. Okay. So it's not planar anymore. But I hope you understand how do we get this volume. Okay. So this also gives us an idea of you have the obstacle, which is shown here, and you have the robot, which has a particular angle. And when the robot is rotating, for each of those rotations, you get a particular shape. And then you stack all of them together and you get your C obstacle volume. So it's a volume now. Okay. Now path planning for a rectangular robot. So when we are doing path planning, we always have to we always have to plan in the configuration space. Okay, so we have to increase or enlarge the size of the obstacle and decrease the size of the robot. Now let's look at this particular example where you have a rectangular robot and this is rotated at 45 degrees. So you can imagine that we place the robot here, okay, go in like this, okay, so it can rotate, it can slip around this point, right? So the robot is here, then the robot is there. Okay, so it can come down in this configuration. Okay, so the robot can move. What are we tracking? Please note where is the origin. The origin is in the center of the robot there. So we are tracking the center of the robot. Now you can imagine that there is an incline here, there's an incline there, there's an incline there, there's an incline there. Okay, so this is inclined by 45 degrees, right? So what will be the shape of this fellow? The shape of this, the shape would be something like this. Okay, so you can imagine that on this side it can slide. So what you're getting, the CG is sliding like this. Okay, then it's moving slightly here. You can move that side. Then again it's sliding. Again it's sliding here, moving here, moving here. So we are basically tracking the CG of the robot now. And as the red robot is moving around the obstacle, you can see that we are tracking the CG and this is the shape that we get. So what is the shape? The shape will be like this. So this is C obstacle. So if I change this 45-degree angle, this shape will change again. Okay, that is logical, isn't it? So for example, in this case, it is like this. It is facing this side. Okay. And suppose it can translate and rotate. Now, if it can rotate, obviously, for every rotation, there will be a different C space. Okay. So what we are doing is essentially, in a case of 2D possibility, it can rotate and translate. Then in that case, what we do when we track what we are getting, because it can rotate also now and translate, what we'll be getting is this my C obstacle. Okay. Now, A problem for finding a path from start to goal point. Suppose this is my goal point. This is a rectangular robot, right? This is a rectangular robot. Okay. And this is my initial point and this is my goal point. And these are obstacles. So this is my obstacle, that's also obstacle. So what we can do is I can assume this robot to be translating only around the obstacles, and then I can make my C obstacle. Okay. So what I'm doing is basically I am making this fellow go and sit like this, go and sit here. I can make it sit like this, then it can translate this side, come and sit till here. What am I doing? I'm tracking the CG of this obstacle. Okay, no, sorry, the CG of the robot when it is moving. So when I track the CG of the robot, what I do get is this is my C obstacle, the shape of the C obstacle. In the center, please note that when it is going and sitting in there, the whole space is going. Okay, which basically means that is why it is. So in the center also, the robot is unable to go through the center. Now we have made our C obstacle. Okay, so this is my C obstacle. Now the robot has become a point, the obstacle has enlarged. So this is basically my C space also with the C obstacle. The robot has become a point. Okay. Now when I want to go from Q goal to from initial point to final point, it is very easy to see that there is free space. This is my free space and this is my obstacle space. So wherever there is free space, it can very easily connect the free space to the goal. And there are that many paths. In this particular case, it can go like this, it can go like this. It can also go from the other side. Okay, so it can also go from this side and go like this also. Okay. So there are a large number of paths. So there are infinite paths. Okay, so there are infinite paths. Then the question comes, which path is faster, which is shorter length. But something to note here is that suppose we are trying to solve the problem in this space. Okay, now if I asked you, can the robot go from here? It's very difficult to say. Okay, because we are relying on our visual data and we are guessing. Okay, so for example, if this is the robot, you'll have to see whether it will fit in. It doesn't look like it will fit this and this. It doesn't look like it will fit there, so it can go. But here it is very clear. In this particular case, it is extremely clear which is free space and which is obstacle space. So very easily it can go in the free space only and connect the initial point to the goal point. Okay, so this gives you the advantage of using C space, where the robot has been converted into a point and the obstacles have been enlarged and they have become the C obstacles. Okay, so path planning is done in configuration space or C space. Now, in the previous case, the robot was like this. Now, in the second case, suppose I rotate the robot by say 60 degrees. In that case, my C space obstacles, C obstacles become like this. Okay. Now, in this configuration, can the robot go through here? Yes, it can go. It can go from here. It can go like this. It can go here. Okay. Now, also it is very clear that what are the various paths possible. Now, this also indicates that for every angle, you will get a particular shape. So, for every theta, you will get a C obstacle shape. Okay. So we can vary from theta is equal to 0 degrees to 306 degrees, get different shapes and then stack them up like this, and this we get a volume. So this is my C obstacle volume, right? So this gives us an idea of the C obstacle and also the C obstacle volume when the robot can rotate and also translate. Now doing this, we can have rigid bodies moving along the C obstacle at different orientations. So for example, this is this is the shape. So it is shaped something like this. And I want to move it from here through this to there. Okay. So this is what we do, that we can move this rigid body with different orientations and take it from the initial point to this goal point. Similarly, moving a piano, which we said that the original motion planning problem started with moving the piano from one room to another. So in this case also, what we are doing is we can take the piano like this, like this, like this, like this, and take it there. Okay, that was the original motion planning problem. Okay, now let's move on from here to the next part, which is the Configuration space or C space for a serial arm. So far we have been talking about mobile robots. Now I'm sure you can also guess why we are talking about mobile robots. First of all, they are circular mobile robots because it's very easy to see the C space. Okay. Now path planning also for a circular robot is easy. Why? Because it's circle. So we can simply check where the circle can go and where the circle cannot go. That's it. Even if it is rotating, it's still a circle. Okay. The moment you make it triangular, then the problem of rotation starts coming inside. But for a serial arm, it's more difficult. Why? Because we said that the obstacle or the robot not hitting the obstacle means that no point of the robot should be inside the obstacle. Let's take an example here. So here we have a mobile robot, so we have a serial arm here. Now we are talking about serial arms. Okay, very simple 2 degree of freedom serial arm. There is one arm here and there is another arm there. 2 arms. Okay, this is 2 degree of freedom, planar. Let us say we have an obstacle here. That's my obstacle. That's an obstacle. Okay. Now we say that robot should not hit the obstacle. Should not hit the obstacle. What does it mean? It basically means no robot, no point of the robot should be inside the obstacle. This is what it means. In the case of mobile robot, it was very easy. Okay, you could understand, shrink it to a point and then you can see that is the obstacle space, that is the C space obstacle, and then no point is inside there, so it's very easy. Okay, so all I have to do in terms of geometry is if I have a mobile circular robot and I have an obstacle like this, all I need to do is shrink this fellow, okay, to a point, reduce by r, decrease that one by r. Okay, so this has come down by r. I inflate my obstacle by r. Okay, this I make it the obstacle. Now I have free space and I have obstacle space. So if I want to go from this point to that point, I can simply go like this. Okay, geometrically, you're just moving a point around, and the point should not go inside here, which is very easy also. You know what are the vertices of this C obstacle. So this point should not go inside there. Okay. Now how do we do that in the case of a serial arm? Now in the case of a serial arm, suppose I want to go from this point to this point. How do I go? Okay. And how do I specify that no point of the robot is inside the obstacle now? Okay. So suppose the point is here. Can I go there? Or I can't go there without hitting the obstacle? Okay. How do you figure that out? Okay. So when we are saying path planning for serial robot arms, we basically mean the robot, no point of the robot link, no point on the robot link should be inside the obstacle. Okay, that is what we mean. So how can I figure that out? Is essentially by doing my forward kinematics. For example, let us look at this, my robot arm. This is my arm, 2 degree of freedom I just drew. So this is L1, this is L2, this is theta 1, that is theta 2. This is my theta 2. Okay, this is my point XY. This is my obstacle. Also, this is my obstacle. I want to go from this point to this point now. Okay, so I should be able to figure out. Now I have my point XY. Now I know that X is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Okay, plus Y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay, so at any point in here, I can do forward kinematics. This is my forward kinematics. I can give different values of theta 1 and theta 2 and then see where the end effector is. Now, if I know this is my XY, I also know from these two equations, I also know that my position is probably here like this. This is one solution. Okay, so for every theta 1 and theta 2, I exactly know where is the end effector and where is this fellow also. So let me call this x1, y1. No, sorry, x1, y1. This joint. Where is this joint and where is this joint? I can find that from these two equations, right? For different values of theta 1 and theta 2. And then I can see by connecting with a straight line if this line is inside that obstacle. That would mean that it's hitting the obstacle. So I'm trying to explain here what is hitting an obstacle mean here. Okay, so I can get different values of theta 1 and theta 2. I can find where is xy and where is x1, y1. That is the position. 0, 0 doesn't move, it's always there. And then I connect by straight lines and say that the straight line is not intersecting with that obstacle. Okay. Now I can go in the reverse direction. For every point, I know what is theta 2. From inverse kinematics, from my inverse kinematics, I have done x squared plus y squared minus L1 squared minus L2 squared divided by twice L1, L2. I get theta 2. So I get cos theta 2. I convert that to sin theta 2. Okay, I convert it, and then I can find what is theta 2 by means of a tan 2. Okay, this we have done in inverse kinematics. Once I get theta 2, I can get what is theta 1 from geometry. That means for every point in this workspace, I can get theta 1 and theta 2. So for all points, I can get theta 1, theta 2. Okay, that will take me to that point. And then what I can do is I can check if this link is intersecting the obstacle. Okay, and then what I can do is I can draw my C-space obstacle. So let me explain how we are going to go about it. So I have theta 1 and theta 2 here as shown here. This is my L1, L2. Okay. Now from that equation, x is equal to L1 cos 1 plus L2 cos 1, 2, and y is equal to L1 sin 1 plus L2 sin 1, 2. I can get the point xy. Now this point is x1, y1. How do I get that? I get x1 is equal to L1 cos 1, okay, and y dashed is equal to L1 sin 1. Okay, so I have got these 2 points. This is joint, or this is not joint 2. This is joint 2. This is end effector point, end point. Let's call it P. This is my end point P. Okay, so I've got this and I've got this. I've got these 2 points. Then what I can do is I can join with a straight line. I've got points, right? And 0, 0 is always there. So I join with straight lines and I check if this is intersecting with an obstacle. Suppose there's an obstacle here and my link has become like this. Now what is happening? This is intersecting with this now. Okay, so there is an intersection now. So the objective is to find free space and obstacle space. Now please note here that generating the C space now is I am generating a circle. This is my theta 2. Okay, so this is my theta 1. It can go from 0 to 180 degrees. So theta 1 can go from 0 degrees to 360 degrees. Okay, so it goes from 0 to 360. It's a circle, right? What about theta 2? Theta 2 can also go from 0 to 360 degrees. So it's like saying that when theta is equal to 0, it is here. This is my theta 1. Okay. Now theta 2 can go from 0 to 360. It's going from 0 to 360. So I get a circle. Then I move theta 1 by next angle, which is here. Then I move it by some more angle. So theta 1 moves from 0, 1, 2, 3. And each of this, theta 2 can go from 0 to 360. So it's like saying this circle is actually going around like that. So at every point here, right? Okay. So this is my theta 2 has gone from 0 to 360 degrees. And this my theta 1 has gone from 0 to 360 degrees. So on this circle, it is theta 1. Okay. And for every theta 1, there is a theta 2 which is going around. Okay. So what we are getting is a shape like this. Okay, this has become very clumsy, so let me draw it again. This is something you need to understand very clearly. That you can imagine that theta 1 is going to go from 0 to 360 degrees. And for each theta 1, theta 2 can go from 0 to 360 degrees also. Okay, so we start off by saying theta 1 is at 0. So theta 2 can go round like that. Okay, it takes a circle. Then theta 1 goes to the next point, which is theta 1 equal to 1 degree. Now this theta 2 can take a circle again there. And similarly, it is taking circles like this, and it is going round like this. Okay. Now if I join these circles, what do we get? We get the shape which is basically called a torus. Okay. And this is my a C space obstacle. Sorry, this is my C space. Okay. So basically what we are seeing here is that the shape that we are getting is that of a torus. Okay. And the C space here and the Cartesian space, they look completely different. The Cartesian space is my x coordinate here and my y coordinate there. Right. Whereas the torus is looking completely different from my Cartesian space now. This is my C space. So the C space and the Cartesian space, they look completely different. In the case of the mobile robot, they look same. Okay, but here they look completely different. Now this is the shape of configuration space for a serial arm. Okay, for that of a mobile robot, it is like this only. This is my x and this is my y. It looks like the Cartesian space. Whereas for a serial arm, what we are seeing is that we have this going this side. This is my theta 2 and that's my theta 1. So that's my theta 1 and that's my theta 2. Okay. So it's like saying this theta 2 is a circle which is going round like this. And sorry, theta 1 is going round like this. And for every theta 1, there is theta 2 which is like this. So if I take the complete, if I take that complete volume, it becomes a torus. Okay, this is something like a cycle tube. You must have seen the tube of a cycle. It's inflated, or a motorcycle tube. Okay, which is inflated. It looks like this. Okay. This is the shape of the configuration space of a serial arm, which looks very, very different from that of the mobile robot. Okay. So our Cartesian space of the mobile robot looks like the Cartesian space. If this is my x, that's my y. So this is one link and that's another link. So this is my x and y. So it looks like the Cartesian space. Whereas the C space looks like this. And it looks very, very different. Okay. So please note that in the case of the mobile robot also, they are different actually, but they look same. Here they look different and they're different, of course. Now this is an example of the torus. So we start off from let me have a look at that again. So here we start off at a point theta equal to, it's a circle which is going around this, so it is becoming a torus. Okay, let me look at it again. Okay, so first of all, at a point theta equal to 0, we have a circle. Theta equal to 0, we have a circle. Now the circle, as theta 1 is changing, the circle is also moving like that. So what we are getting is this kind of a structure, which is basically a torus structure. So please note that in the case of a serial arm, the shape of the C space is that of a torus. Yeah, so in the case of a mobile robot, they look the same, C space and Cartesian space, but they are different. In the case of the serial arm, they are different and they look different. So in the next, we'll stop here today, and in the next class, what we'll do is we'll look in more details as to this torus structure. Why? Because when we are doing path planning, we are finding the path on the surface of this torus now. Okay, and when we talk about an obstacle, we have to plot the obstacle on this torus only. Okay, because that is the C space of the serial arm is a torus. Okay, so we'll stop here today and we'll continue in the next class regarding drawing the C obstacle for a serial arm, and then we'll look at planning. How do we plan? What does it look like? And how do we do the path planning for a serial arm?